Here is class 4, and this is like part 6. Is that true? That's crazy. How many parts do I have? I guess this is part 7. Darn. I'm going to get rid of some stuff. You see that we're going to use these gear forces for something, but here it is. Yeah, here's the gear force, WT, the transmitted gear force, or tangential, if you will, that we apply. You can see that as force is being applied onto the gear, this is how it we arrange it. Okay, so here's an example. Gear force and power examples. Okay. So this is the remainder of problem 1333. So we said, what forces do gears 3 and 4 transmit to their idler shaft, right? So there's a shaft right here, and we want to know what the forces are acting on the shaft, right? So there's the operative word. So we know that it's 150 kilowatts that's happening right here. So this is this guy right here is clockwise, and N2 is or the shaft at N2. Yeah, but the N2 as well. So 180, 1,800 RPM clockwise. The power is 150 kilowatts, right? And we're trying to find the forces that are on 3 and 4. So previously, we can look up that video. Previously, we found that E on this thing was 18, because it was 18 teeth. They're both drivers, driven at 32 and 48. So we got 0.2109 was the gear ratio right there, and that allowed us to find out that the output gear, aka the output shaft as well, was going to be 379.7 RPM, right? This had a module of 12 millimeters, so we multiplied 12 by 18, 12 by 32, 18 again by 48. So we know that the diameters of each of these were going to be 216 millimeters, which is also what D4 was. D3 was 384 millimeters, and D4 is 576 millimeters. I say was, but it still is, right? Okay, so I'll draw my free body diagram, FBD, of, I guess, I'll draw it of both of the gears right in here, right? Because we're looking for the idler shaft here, so let's draw this. And right here, and looking at the forces that are acting on gear 3, see, I'll kind of make it a little very light right there. Gear 3 is being turned that way, so it's being pushed in that way. So this is the force of gear 2 on 3 in the tangential direction. Here's the force of 2, 3 in the radial direction. And then we see 5 right here. Okay, so it's better to like draw which, on this, well, one thing is there's no torque onto this shaft right there, right? Not as it's being drawn. Like we're saying that these two gears are connected to each other. So it has to balance out. So this is one way that we could think of the thing, is there's going to be a force coming this way, because this one's trying to make it go counterclockwise. This one should make it go clockwise, and that should be the force of 5 onto 4 in the tangential direction. And then there's also going to be the force of 5 under 4 in the radial direction. So they say, well, let's figure out what that force has to be on 2, 3, right? So the force of 2, 3 is going to be in the tangential direction, is going to be equal to the same thing that we found. Let's see, which equation are we using? We're going to use equation 1336, which trying to find where it is. Yeah, 1336, because we're dealing with kilowatts right here. Here's kilowatts right here, and we want to get this transmitted. So that's the one that we're going to use. Which is, so I'm going to, I think it was a subscript here, the WT in that equation, 60,000 times H divided by pi D and N. Okay, so 60,000 times 150 divided by pi divided by the diameter. So we're going to use the diameter of the pinion right there, right? Because we know it's RPM and we know its diameter. So we have to make sure we're always using the correct combination, because these forces will be dependent on what the diameter is and the RPM along with the power right in there. So the diameter of this, and notably that this equation uses millimeters for this. So that's another thing that we want to double check that we're using the right units. So 216, and then the RPM is 1800. So we get that it's, and the answer of this comes out into kilonewtons, 7.368, 8 kilonewtons. And then in the radial direction, we take F23 and multiply it by the tangent of the pressure angle right here. And so if we do the 7.368 tangent of 20 degrees, we get 2.682 kilonewtons. Okay, so we could use the sum of the moments and find out what this this force is going to be, right? That's applied right in there. And I haven't finished this, by the way. I also need to write out what the reactions are going to be right here, that are right here on these right here. And I don't know, by the way, that they're in these directions just yet. Maybe I'll write them on here. Here's the force of shaft B. And I'm not going to, it's on both B3 and 4, so I'm just going to write the shaft force B right in there. And I'll call that the Y direction, and the shaft for a B in the X direction, acting right on there. I wanted to make that complete, but let me finish by finding this force right here. Like, once again, I said I could use the sum of the moments and about this point right here and find what that is, but let me instead go that the force 5, 4 in the tangential is going to be another transmitted force. I don't want to say that it's WT because it's going to be a different force, but that's going to be 60,000 times our 150, and it's divided by pi. It's going to be the diameter of the output gear, right? Or did I write that wrong? I think there's supposed to be a 5 right up there. Yep. Oops. So that's going to be 576, and it's going to be times our 379.7 right here, and what we're going to find is a 13.099. Okay, 5 sig figs. So the 5, 4 in the radial direction is just going to be that 13.099 times the tangent of 20 degrees. So we get 4.6768 kilonewtons. So now, to be able to answer the question here, we take the sum of the forces in the x direction equal to 0, right here, right? And as I've written it out here, I say that it's the force FBX right there, and plus our force right here, which is going to be what that was supposed to be radial. That's supposed to be a radial. Yeah. Okay. That's tangent. This is not being okay. So it's this 7.368, right? And then this is minus, and that's that radial. So that's 4.768 equals 0. So we're going to end up with an FBX. I believe it's going to be negative 2.6 kilonewtons. So that's going to be in the opposite direction as drawn. We drew it wrong, but we had to assume something. And then we take the sum of the forces in the y direction. And looking right there, we have FBY plus our, I guess I went to this one first. So it's the 23R, 2.682. And then here's in the tangential direction off of this one. So it's going to be a minus 13.099. For some reason I had an extra thing. So FBY is going to be a positive 10.42 kilonewtons. So the answer here, the force is on there. Let's just say that it's going to be the force of B as a vector right here. We'll say that it's going to be in the negative direction in the horizontal, and it's going to be in the positive direction in the vertical. And once again, and these are kilonewtons. These are the force. These are the forces applied to the shaft, right? So if you wonder what the no, my bad. Yes. Okay. So sad panda. Oops. It should be opposite. These are the forces of the shaft onto the gear, right? It's happening onto the gear, but we want to find the forces that are happening onto the shaft, so we have to get the opposite direction. Now we're okay. Yay! It's an important thing to keep track of. So there you go. I think I could have done this whole thing with giving you less information in a short amount of time.